Hello and welcome again to my Physics Online video lecture series. In today's video, we're going to be introducing the concept of linear momentum. We will also be not only defining it, but maybe working a few problems with it. And then in future videos, we will discuss things like impulse, which is the change of linear momentum, and introducing a new conservation law and using it to solve problems involving simple collisions. At this point in the semester, you should have already worked through, or if you're following my videos on your own, you should have already watched my series about forces, my series about vectors and vector resolution, and my series about kinematics. Now, in most textbooks and most semester schedules, you also would have gone through work and energy at this point. Some of them also place centripetal motion before this point. Others do this before those two subjects. So depending upon if you're taking this as you're watching these because you're one of my students in one of my classes and following the book, you should be following the order that the book is in. If you are instead just doing this for the fun of it or taking somebody else's course, then welcome, but you may or may not have covered work and energy and for that matter centripetal motion, which is maybe a little less important to this week's or this today's discussion, this set of videos discussion. As a general thing, I will try to avoid talking too much about work in this video, simply because there are some textbooks that introduce momentum before they introduce work. In fact, there's a very good algebra-based physics textbook by Knight, I think it's Knight, Jones, and Field or something like that, or Knight and Jones, which introduces momentum before introducing work and energy. The standard approach is to introduce work and energy first. So once we get into discussing collisions, I will discuss both momentum and work just because at that and energy, just because at that point it's important, but at this point it's not so important. So you can recall either way Newton's force laws. So Newton's force laws govern forces and how they interact with matter. The other thing that you should recall besides Newton's force laws is that there are vector quantities and scalar quantities, and that vector quantities must be dealt with slightly differently than scalar quantities. Okay? Now, one of the things from Newton's force laws when I introduced those was that I said that the net force of a system can be zero if the system is in equilibrium, and that, on the other hand, forces tend to change the quantity of motion. So you may recall that from the force discussion. At that time, for example, we did Newton's second law, which said F equals ma. The force is the mass of the object times the object's acceleration, or the net force on the object should be its mass times its acceleration. And I noted at the time that this was an incomplete description of what's going on when you apply a force to an object. So here we can actually expand on that a little bit by introducing a new quantity, which is a sort of, you can think of it in some ways as like the quantity of linear motion. It tells you how much stuff is moving for an object, how fast it's moving, and what direction it's moving in. Okay, so those three things combined give us this quantity called momentum, or linear momentum. In equation form, we would say that linear momentum is defined as the mass of the object times its velocity. So linear momentum, we represent linear momentum with the letter P. And notice that it is a vector quantity the direction is determined by the direction of the velocity vector. So this is your definition equation. This is what momentum is. Okay, how much? That's the m. How fast? That's the magnitude of the v. In what direction? That's the direction of the v. Okay, so this is your linear momentum. Therefore, a larger object moving faster will have a larger momentum than a smaller object which is moving more slowly. Now note that it's a vector quantity and therefore it has a magnitude and a direction to it. The unit, for what it's worth, is the Newton second, or at least in the MKS SI system, Newton second. That also gives us a hint as to where this equation is going to come into play when we get to discussing impulse. Okay, so for right now, we know that this right here must be somehow linked to this equation because we know that acceleration represents a change in velocity. But as I've said, there's a little more to it, and that's getting a little ahead of myself. So linear momentum is mass times velocity. And that's how we define linear momentum. There's not much more to that as such. It's a very powerful tool, as we will see in future videos, for doing things like figuring out if there is a head-on collision between two objects, or if there's a initially stopped object and another one collides with it. How will those two objects move after the collision? But again, that is for another video on another day. Let's do a quick example and maybe make this a short video. In our example, we want to determine the magnitude of the linear momentum of two objects. One is a bullet and the other is a rock. So the bullet is 25 grams traveling at 280 meters per second. Magnitude, remember, is just taking the magnitude of the two quantities m and v that are present in the definition for momentum. So we would have 25 grams. 25 grams, however, should maybe be converted over to kilograms, so times 10 to the minus 3 kilograms per gram times 280 meters per second. All right, so this gives us a total of, should be 7 Newton seconds. The second object is a 2 kilogram rock which has been thrown at 24 meters per second. So we have 2 kilograms times 24 meters per second. And so 2 by 24 would give me 48 Newton seconds. That's almost 7 times as much momentum as the bullet had. Now, you may be a little surprised by this, and in fairness, bullets maybe travel a bit more than 280 meters per second, but even if you double the speed of the bullet, you're looking at 14. You're still more than 3 times larger value for this 2 kilogram rock, which is a fairly hefty rock to be throwing at 24 meters per second. But it's kind of surprising on a first glance that the rock would have so much more momentum than the bullet. But bear in mind that that rock is a lot more massive. That's all I'm going to do in today's video. It is short, shorter than most of these have been, but hopefully it has been informative. Hopefully you learned something from it. And in the meantime, thanks for watching.